Hello, and welcome to the channel. Have you ever imagined a key that could unlock the deepest secrets of the universe? A tool so powerful it could design life-saving drugs in a matter of days, not decades? A machine that could accurately predict the chaotic dance of our planet's climate, giving us the clarity we need to save it. What if I told you this isn't a fantasy from a distant future, but a reality being built right now, in labs all across the world? This is the story of quantum computing, and it's a revolution that will redefine everything you thought was possible. Stay with me, because by the end of this journey, you'll not only understand this incredible technology, but also see your own world in a completely new light. Let's start with a vision. Picture a computer so immensely powerful that it could solve problems in mere seconds that would take today's fastest supercomputers, machines that fill entire rooms, billions of years to even begin to crack. Imagine what that power could do. It could reshape medicine by simulating molecules with perfect accuracy, leading to cures for diseases like Alzheimer's and cancer. It could shatter modern cryptography, the very foundation of our digital security, but also give birth to a new, unhackable internet. It could create financial models that predict market crashes with eerie precision, or design new materials, atom by atom, to build hyper-efficient batteries and solar panels. This isn't science fiction. It is the concrete, tangible promise of quantum computing. We are standing at the edge of a computational cliff, about to take a leap into an entirely new dimension of problem solving, one that will fundamentally alter the fabric of science and society itself. 2. From prediction to progress. The revolution is unfolding. For decades, quantum computing was the stuff of chalkboards and theoretical physics papers. But that era is over. The technology is rapidly moving from the lab to the real world. Visionaries and industry titans, people like Bill Gates and Google's CEO Sundar Pichai, are not speaking in terms of if, but when. They see quantum computers achieving real-world usefulness within just a handful of years, drawing a powerful parallel to where artificial intelligence was just a decade ago. Think about that. A decade ago, AI was a niche field. Today, it's in our phones, our cars, and our homes. Quantum computing is on the exact same trajectory, but its impact could be even more profound. The revolution isn't a distant storm on the horizon. The first raindrops are already falling. We are living through the transition from a theoretical dream to an engineering reality, and the pace is only accelerating. You might be thinking, this is fascinating, but what does it have to do with me? I'm not a physicist or a computer scientist. The truth is, quantum computing will touch every facet of our lives. Just as the internet and the microchip redefined every industry, this new wave of computing will have a universal impact. It will influence how your investments are managed, creating new strategies for financial markets. It will change the way we educate our children, introducing them to entirely new ways of thinking about information. It will transform agriculture, logistics, and manufacturing. Soon, quantum computing will be working behind the scenes in nearly every field imaginable. In this rapidly approaching future, understanding the basics of this technology won't be optional for the curious. It will be a fundamental part of digital literacy, as essential as knowing how to use the internet is today. Staying relevant in the coming technological shift means getting acquainted with the quantum world now. So, what is the magic behind it all? To understand it, we first need to look at the computers we use every day. From your smartphone to the most powerful supercomputers, they all speak the same language, the language of bits. A bit is like a light switch. It can either be on or off, a 1 or a 0. It's a simple binary system, and for decades, we've just found clever ways to stack billions of these switches together to do amazing things. Quantum computers, however, speak a completely different and far richer language. Instead of bits, they use qubits. Now, a qubit can be a 0 and it can be a 1. But here's the mind-bending part. Thanks to a quantum phenomenon called superposition, a qubit can also be both 0 and 1 at the same time. Imagine a spinning coin. While it's in the air, spinning, it's not heads. And it's not tails. It's in a state of potential, a blend of both possibilities. It's only when it lands, when we measure it, that it settles into a definite state of heads or tails. A qubit in superposition is like that spinning coin. It exists in a cloud of probabilities, a fluid state of both 0 and 1. This single foundational idea, that a unit of information can exist in multiple states at once, marks a monumental departure from classical computing. It's not just an upgrade, it's a whole new paradigm for processing reality itself. If the idea of one qubit being in two states at once is powerful, imagine what happens when you bring multiple qubits together. This is where the true, exponential power of quantum computing is unleashed. If you have two classical bits, they can represent one of four possible combinations, 00, 1, 10, or 11, but only one combination at a time. Two qubits, however, can represent all four of those combinations simultaneously. Add a third qubit, and it can represent 8 states at once, a fourth, 16. This power grows exponentially. With just 300 qubits working together, a quantum computer could represent more possible states than there are atoms in the observable universe. Let that sink in. A machine that could hold, in its processors, more information than every star, planet, and dust cloud in existence combined. This isn't just about doing calculations faster. It's about exploring an astronomically vast landscape of possibilities all at once. It's this exponential scaling that allows quantum computers to tackle problems of staggering complexity, problems that are, and always will be, utterly impossible for any classical computer to solve. So how do quantum computers actually harness this bizarre quantum world to get useful answers? They use a toolkit of 3 incredible phenomena, 3 of nature's secret weapons: superposition, entanglement, and interference. We've already touched on superposition, which allows qubits to exist in multiple states at once, giving them the power to explore many solutions in parallel. Next is entanglement, a phenomenon Albert Einstein famously called spooky action at a distance. When two qubits are entangled, they become deeply connected, their fates intertwined no matter how far apart they are. If you measure one qubit and find it's a 0, you instantly know its entangled partner will be a 1, and vice versa. It's as if you have 2 magic coins. You give one to a friend who travels to the other side of the universe. The moment you flip your coin and it lands on heads, instantaneously, that theirs has landed on tails. This connection allows for incredibly sophisticated and correlated computations across the entire processor. Entanglement links qubits into a single, cohesive computational entity, making the whole vastly more powerful than the sum of its parts. Finally, there's interference. Just like waves in a pond can reinforce each other, constructive interference, or cancel each other out, destructive interference, a quantum computer can manipulate the probabilities of its qubits. The quantum algorithm is cleverly designed so that the pathways leading to the wrong answers cancel each other out, while the pathways leading to the correct answer amplify each other. Think of it like a pair of noise-canceling headphones for computation. It filters out all the noise of incorrect solutions, leaving only the clear signal of the right answer. By masterfully weaving together superposition, entanglement, and interference, a quantum computer can navigate a vast ocean of possibilities and emerge with the one answer it was looking for. If quantum computing is so powerful, why don't we have them on our desks already? The answer lies in its greatest weakness: fragility. The quantum states that give qubits their power, superposition and entanglement, are incredibly delicate. The slightest disturbance from the outside world, a tiny vibration, a stray magnetic field, or a fluctuation in temperature, can destroy the quantum state in a process called decoherence. The quantum magic vanishes, and the qubit collapses into a boring old classical bit, introducing errors into the calculation. To protect these fragile states, quantum computers must be shielded from the universe. This means operating them in extreme conditions, inside heavily shielded chambers cooled to temperatures near absolute zero, colder than the vacuum of deep space. Even with all this protection, errors still creep in. The current generation of machines are known as NSQ systems, which stands for Noisy Intermediate Scale Quantum. They are powerful enough to perform tasks beyond classical computers, but are still plagued by noise and errors. Their calculations can only run for incredibly short periods, a fraction of a second, before decoherence kicks in and the quantum state is lost. Overcoming this fragility and building effective error correction is the single biggest challenge standing between us and the full promise of quantum power. For years, the problem of quantum errors seemed like a catch-22. Adding more qubits to make the computer more powerful also added more sources of noise, making it less reliable. But in late 2024, Google Quantum AI announced a monumental breakthrough with its new processor, the Willow chip. The Willow chip, a 105-qubit processor, was the first to demonstrate a crucial milestone. It could actually reduce error rates as it scaled up. This achievement in quantum error correction showed that building large, reliable quantum computers is not just a theoretical dream, but an achievable engineering goal. The team demonstrated that by bundling physical qubits together to create a more robust, logical qubit, they could actively detect and correct errors, allowing the quantum information to survive for longer. To showcase its power, Willow performed a benchmark calculation in under 5 minutes that would take even the fastest supercomputer on Earth an estimated 10 septillion years to complete. A number so vast it's longer than the age of the universe itself. The Willow chip doesn't solve all the problems of quantum computing, but it represents a critical turning point. It's a sign that we are finally starting to tame the chaos of the quantum realm, bringing us significantly closer to building fault-tolerant quantum computers, the holy grail of the field, systems that can run long, complex calculations reliably. Quantum computers won't replace your laptop for writing emails or browsing the web. They are specialized machines designed to tackle specific types of problems, namely, problems involving immense complexity, simulation, and optimization. Here are a few of the industries they are poised to revolutionize first. Drug discovery and medicine. At its core, biology is a quantum system. The way proteins fold and interact with drug molecules is governed by quantum mechanics. Classical computers can only approximate these interactions, which is why drug discovery is so slow and expensive. A quantum computer could simulate these molecular interactions with perfect fidelity, allowing scientists to design new drugs and personalized medicines with unprecedented speed and accuracy. Finance. Financial markets are incredibly complex systems. Quantum computers could revolutionize the field by running sophisticated models to optimize investment portfolios, price complex financial derivatives, and detect fraudulent activities with far greater accuracy than today's algorithms. Climate change modeling. Our climate is one of the most complex systems we know. Quantum computers could create incredibly detailed and precise models of global weather patterns and oceanic currents, giving us a clearer picture of climate change and helping us develop more effective strategies to combat it. This could also lead to breakthroughs in designing more efficient batteries, better catalysts for carbon capture, and new materials for renewable energy. Cryptography. This is a double-edged sword. A powerful quantum computer could break most of the encryption standards we rely on today to protect everything from bank accounts to government secrets. However, quantum mechanics also offers the solution. New forms of quantum-safe encryption, like quantum key distribution, QKD, which are theoretically unhackable. The race is on to develop these new standards before the threat becomes a reality. The world's superpowers understand the stakes. The nation that masters quantum computing will gain a significant economic, scientific, and strategic advantage. Consequently, a global race for quantum supremacy is well underway. Governments and corporations are pouring billions upon billions of dollars into research and development. The United States, China, and the European Union are leading massive government-funded initiatives to accelerate progress. In China, the government is reportedly investing over $15 billion into a national quantum lab. The US and EU are also investing billions to foster innovation and build a quantum-ready workforce. Meanwhile, a fierce competition is raging in the private sector. Tech giants like Google, IBM, and Microsoft are locked in a battle to build the most powerful and stable quantum hardware. They are joined by a vibrant ecosystem of ambitious startups like IonQ and Rigetti, each exploring different physical approaches to building a quantum computer. from superconducting circuits to trapped ions and photonics. This intense competition, fueled by both national ambition and commercial opportunity, is rapidly accelerating the pace of innovation and pushing the entire field forward at an incredible speed. The arrival of quantum computing won't be a single event, like flipping a switch. Instead, we'll see quantum advantage, the point where a quantum computer can solve a real-world problem better, faster, or cheaper than a classical computer, emerge in stages. In the next few years, now to 3 years, the first signs of quantum advantage will likely appear in optimization problems. Think of logistics companies optimizing shipping routes or financial firms fine-tuning investment portfolios. Early, noisy SENISQ machines will be used to find better approximate solutions to these complex puzzles. In the medium term, 5 to 7 years. As machines become more stable and error-corrected, we'll see breakthroughs in molecular modeling and materials science. This is the stage where quantum computers could start making a real impact in drug discovery and the development of new materials for batteries or solar cells. In the long term, 10+ years. This is the timeline experts often cite for the arrival of large-scale, fault-tolerant quantum computers capable of breaking current encryption standards. It's crucial to remember that quantum computers will not replace classical computers. They will work alongside them in a hybrid model. Your laptop will still handle everyday tasks, while complex problems will be sent to a quantum processor in the cloud, which will return the solution. They are not competitors, but powerful complements, each excelling at what it does best. Despite the breathtaking speed of progress, the road to a truly practical, fault-tolerant quantum computer is still paved with significant obstacles. The journey is far from over. The biggest challenge, as we've discussed, remains the high error rates caused by decoherence. Building robust quantum error correction that can work at scale is a monumental engineering task that will require further breakthroughs in physics and materials science. Beyond the hardware, there are software and human challenges. Programming a quantum computer is fundamentally different from classical programming. It requires thinking in terms of probabilities, superposition, and entanglement. We are still in the early days of developing quantum algorithms, and the software tools needed to run them effectively. Finally, there is a global shortage of quantum talent. There simply aren't enough physicists, engineers, and computer scientists with the specialized knowledge needed to build, program, and operate these complex machines. Bridging this skills gap is essential to fueling the next stage of the quantum revolution. The good news is that the entire global community is working to tear down these barriers. Every challenge is being met with a wave of innovation. Breakthroughs in hardware, like Google's Willow chip, are proving that error correction is a solvable problem. At the same time, companies are developing more sophisticated software platforms and programming languages, like IBM's Qiskit and Google's Cirq, which make it easier for developers to start experimenting with quantum algorithms. Crucially, access to this technology is being democratized. You no longer need to be at a top research institution to run an experiment on a quantum computer. Companies like IBM and Google offer cloud-based access to their quantum machines, allowing anyone with an internet connection to learn and explore. 30 universities around the world are launching new quantum computing courses and programs, training the next generation of quantum pioneers. This combination of better hardware, more accessible tools, and a growing talent pool is creating a virtuous cycle that is accelerating progress at an exponential rate. So, what can we realistically expect to see in the next 5 years? The quantum landscape is set to evolve dramatically. We will see the rise of specialized quantum cloud services, where companies can access quantum resources tailored to specific problems in chemistry, finance, or optimization. Early, practical applications will start to emerge, moving from research papers to real-world business advantages, particularly in logistics and drug development. On the security front, the transition to quantum-safe cryptography will begin in earnest. As the threat of quantum code breaking becomes more tangible, governments and industries will start rolling out new encryption standards to protect our data for the long term. By 2030, just a few years from now, quantum computing will likely have moved from a niche, experimental technology to a powerful tool that is beginning to redefine industries. Its impact could be as profound and transformative as the internet was in the 1990s. A technology that started in labs and went on to change the world. 15. The big picture. Humanity's quantum leap. When we step back and look at the big picture, it becomes clear that quantum computing is more than just a faster way to do math. It represents a fundamental shift in our relationship with information and with reality itself. For centuries, we have built tools based on the classical laws of physics, the predictable, everyday world we can see and touch. Now, for the first time, we are building technology based on the strange, probabilistic, and deeply interconnected rules of the quantum realm. This is a new way of thinking. It's a tool that allows us to speak nature's native language. By doing so, we could unlock solutions to some of humanity's most daunting challenges. It could give us the tools to cure diseases that have plagued us for generations, to create a sustainable energy future, and to build a truly secure digital world. This is not just another technological advancement. It's one of the greatest intellectual and scientific turning points in human history. It is humanity's quantum leap. The quantum era is no longer a distant possibility. Its arrival feels inevitable. Its waves are already beginning to lap at our shores. Understanding this technology today is like getting a glimpse of the blueprint of tomorrow. It raises profound questions. Will this technology fulfill its incredible promise for good? Or could its power, particularly its ability to break encryption, outpace our ability to control it? The answer to that question will be shaped by how we choose to engage with it now. It will depend on the conversations we have, the ethical frameworks we build, and the curiosity we nurture in ourselves and in the next generation. The future is not something that simply happens to us. It is something we build together. What are your biggest hopes or fears about a quantum future? What industry do you think will be transformed the most? Let me know your thoughts in the comments below. I'm genuinely curious to hear what you think. Thank you so much for joining me on this journey into the quantum realm. I hope it sparked your curiosity and given you a new way to see the world. I wish you all the very best of health. If you enjoyed this exploration and want to keep diving into the technologies that are shaping our future, please consider subscribing to the channel. Until next time,